In this first module, I have one lecture for you, and that is Spark UI Introduction, or really an introduction to Spark, a little under the hood view of how Spark works. We'll get into a little bit of vocabulary, and you'll understand how Spark uses distributed computing to achieve the goals of big data analysis. So what's involved in executing a Spark application? So this Spark application, and maybe this is just one query that's been written, a piece of code that you want to execute. You send it to Spark, and Spark is going to break this up into a number of different jobs. And these jobs effectively are the secret to Spark's performance and that parallelism that Spark is going to take advantage of. Because each job is meant to be executed by one core, right? One worker, one executor. Anything that can make it so that we can parallelize these jobs is going to make things happen faster, right? Because jobs can be done in a parallel fashion. Now, jobs are going to be made up of one or more stages. The stages are run in order, and they need to be executed into essentially a series of steps, right? It's a series of steps that will fulfill the purpose of the job. Now, each stage itself is going to further be broken into specific tasks, and it is these tasks that are actually going to be executed by the worker nodes in a specific core. We're going to talk about that in just a second. So there you go. We essentially have a cluster here. And a cluster is going to be made up of either just a driver, and that's all. The driver is going to carry out all the work. Or we can also add one or more workers, right? The worker nodes. And these nodes then allow us to perform more work in parallel. So we'll have at least a driver, and then the driver can have 0 or more than 0 workers. These worker nodes are going to have an executor, essentially some software on there, that's going to work with the driver to ensure that tasks are essentially carried out, where the driver is going to assign each of these workers through the executor these specific tasks. Now, an executor is going to have one or more cores, and these cores then essentially allow us then to execute the code or the task that's involved. Essentially, you could think of these as a slot where we can put a task in there and have the executor then fulfill that task or implement that task or essentially carry out the task. So the more cores that are involved, the more tasks that can be carried out in parallel. So let's think about how this can be done now in a very simple way. I'm not going to spend a lot of time on this, but imagine now that you've got a class, you got a teacher up front and a handful of students, each of them at different desks. The driver represents the teacher or vice versa. And then you have an executor that is running as a table, and each student at the table is a core. Now we have data that needs to be performed, some data task that needs to be performed. For example, let's filter out the brown pieces of candy in each bag. The bag represents a partition, and the partitions then can be distributed to each core in the executor for that data processing. So essentially what happens now, the driver says, all right, let's distribute these out. I'll give you what needs to happen, and you go ahead and execute those tasks. The executors then execute those tasks using the cores, and eventually we have all of the brown candies filtered out. It's all finished, right? And that was done in parallel, right? Each packet of data was distributed. Students or the cores worked on them all at the same time, and they said, here's the remaining data. We filtered out all the brown candies. Now, what about if we're trying to count the total pieces in all the candy bags? Then we start introducing a stage, right? Because there needs to be an order to this. In Spark, we need to ensure that we perform one task before we can perform the other task, and that's what a stage is all about. So here we go. We want to count the candies now. So what's going to happen now is that each executor is going to get a local count, and then at the end, after all of the local counts have been determined, they'll all report back to the driver and say, here's my local count. The driver then adds them up and says, okay, great, I've got a global count. So there we go. The driver says, great, here's some candies, count them up. And as each node, as each worker, as each core finishes up, says, here's my local count, I'm ready for some more data, I'm ready to count more, then the driver will hand out more work to that specific core. Another count will be done. So you can imagine now, if there's a huge amount of candy, a lot of candy bags that need to be counted, then the greater the number of cores, the faster the work is going to happen. It'll happen really as fast as the slowest worker, right? The core that is working on the largest amount of data is going to finish last, right? And so there's some things that we can do to optimize, right? Ensure that the size of the data, right? The size of the candy bags is about the same. Otherwise, we have one core that's working really hard, and the entire query, right, the whole count is going to go as fast as that slowest one. And if there's a huge amount of data in that one, then that's going to be a problem. We'll talk about that. So there we go. So we have each node now, each executor gets its local count, reports back, and then stage 2 is the global count, where we count up all of the totals, get a global count of all of the candies in the bags. That has to happen after the local counts are finished. We can't get a global count until we know what the local counts are. So we have stage 1 is the local count, stage 2 is the global count. And this is only when there are tasks that need to be performed in order. We'll have some tasks assigned in stage 1, some tasks assigned in stage 2, and these two stages will be sequential. So let's talk about then how Spark can determine how to assign the tasks, or in what order stages need to be performed, or things like that. Essentially that optimization that's built into Spark. We first have that query. We essentially say, I want to execute some query or another. And what's going to happen then is that query is going to be parsed into an unresolved logical plan, essentially just a representation of the query, a little syntax check to make sure that the grammar and the syntax is right, that all is well with that unresolved logical plan. If there's a problem, it'll report back an error and say, you got something wrong with your syntax. Then, as we go to the logical plan, as opposed to the unresolved, we actually have a logical plan. What's going to happen now is that there's going to be an examination of the metadata, the catalog, to determine whether the syntax, the requests that are being made on specific data, there needs to be an analysis of the catalog of data, the metadata, that says, okay, what are the columns, what are the table names, what are the data types, what are the column names, and so forth. We need to ensure that those exist, that it's the right data type, and that everything that's being asked for can actually be performed because the data exists, or that at least the metadata shows that there are tables with those names, columns with those names, and that the data types match. If it passes through that, then we have now a logical plan that says, all right, we're good to go, everything is well. If it doesn't, it'll throw this back and report an error, say, I can't do it, I'm so sorry. It probably won't apologize, but hey, that's the idea. Now, along with this, we have adaptive query execution, which has been enabled by default as of Spark 3.2, where there's also going to be some runtime statistics that are going to help with this logical plan, right? And ensure that the best ideas are going into this logical plan. Once the logical plan has been determined, and we know that the data exists and is ready to go, then we go through the Catalyst Optimizer. Now, the Catalyst Optimizer is going to examine the logical plan and say, hey, what optimizations can I put on this? I know that a person has written this in a specific order. Maybe they're doing some joins. Maybe they're doing some other things. But is there something we can do to optimize this code? Maybe it's predicate pushdown, or other things that can be done to ensure that this is the most optimized set of steps in this logical plan. And again, this is still just a logical plan. We haven't actually determined what the cluster or what the compute is actually going to do. That's what happens when we get to a physical plan now. We'll take that logical plan and say, what is actually going to be done? What does the cluster need to do? What are the stages, right? What are the tasks? What needs to be carried out? And so there's a physical plan that gets implemented from the optimized logical plan. Now note, there's a number of physical plans. I should say plural, right? There's a number of different physical plans, all in a way, maybe there's different ways of seeking to execute the same logical plan. What will happen now is we have a number of different physical plans to choose from. This goes through a cost model to determine what is going to be the most costly, and we'll push that to the bottom. And what will be the least costly, let's have that be the one that we're going to select and actually make that the selected physical plan. And that's based on that cost-based optimization. Right? We look at the cost model and say, what's going to be the most optimized way to execute this? We'll select that physical plan, and then we'll throw it out there and actually execute the tasks and throw them out to the compute and say, go for it, we're ready to go. So as far as your code, here are some things that we would recommend for you to optimize your code in the best way possible. Use data frames or data sets instead of RDDs. RDDs are, we could consider those, think of those as the old school way of doing things. They do not take advantage of the cost-based optimizer. So use data frames or data sets and not RDDs. In production jobs, don't use operations that will trigger an action. right? So actions are the things that actually carry out the work, right? So we can define a data frame, for example, without actually causing a trigger of an action which is actually going to perform work on that data frame. Things like display, right? So if we're running a production job, we don't necessarily have to display the output of a data frame, but that's an action that will cause that data frame to be computed. It'll be calculated, it'll be run. It will take compute time and compute power to do that. Things like collect. Now again, sometimes actions need to take place, and certainly that is true of everything, but there are some things that you will not need to do. They're just there to help you in your coding and your development of your queries, and not necessarily in production. So do take a look at your code and ensure you're avoiding all of those unnecessary operations. Also, avoid operations that are going to force all computation on the driver node using single-threaded or Python Pandas APIs, right? So try and use the Pandas API on Spark instead of distributing to Pandas functions, for examples, right? Single-threaded that goes against everything we want to do. We want to use distributed computing and ensure that we use all of the cores in our cluster to the maximum amount possible. And if we're using single-threaded Python or Pandas execution or methods, then we're going to have a problem. So here's the Pandas API on Spark. I've got a link for you. You can certainly use it. Have a look at how that can be done on Spark, and you can use PySpark to perform those actions, or even better, use SQL if you can, because that already has optimizations.